Okay, students, we are at chapter 10 on alkanes. So we will look at some of the learning objectives which you probably need to be aware of. Okay, I think 11.3a is something which you need to pay a little bit of attention to. Like you will need to explain the general unreactivity of alkanes, especially towards polar reagents. Okay, so even without going into the lecture notes proper, I think at this stage, if I just draw an alkane out, let's say ethane, right? Based on your chemical bonding knowledge, and of course you can search for the information on the data booklet on the bond strength, you'll realize that the CC bond and the CH bond are generally pretty strong and they are non-polar. Yeah, so one of the key criteria for reactivity is that I need to overcome the bond strength between the relevant atoms. Yeah, so if they are relatively strong and they are relatively non-polar, that means that their resistance for reacting with, say, polar reagents such as maybe a nucleophile or even an electrophile. Yeah, and in that sense also make it difficult for them to be oxidized or reduced unless they are being put in very extreme conditions. So these are some of the consideration you need to have whenever you want to look at reactivity. So it's not just about whether the bond is strong or weak, because a strong bond need not be unreactive. So for example, you know that this particular bond, which is called the carbonyl group C double bond O, although the bond is very strong, I think it's close to 700 kilojoules per mole in terms of bond strength, but it is highly susceptible to attack by a nucleophile, especially at the carbonyl carbon, because it takes on a relatively huge partial positive charge. So this kind of bond, when we say that it has a dipole moment, we tend to associate with it with reactivity with nucleophiles. Okay, so if you don't really understand some of the terms I said, like things like nucleophile or polarity differences, all this, you might want to review the earlier topics in chemical bondings. And for nucleophiles, I think it will be good for you to take a look at introductory organic chemistry. All right, so we will just move on in this chapter to look at some of the important details you need. And this is the first time you'll be introduced to the mechanism, and this is probably the only time you'll be drawing mechanism using half arrows, or what we call the fishhook arrows, which represent single electron movement. Okay, so we'll just move on to the first portion on introduction. Yep, so here we have alkanes. So alkanes is part of the hydrocarbon family. Hydrocarbon, as the name implies, only contains carbon and hydrogen and nothing else. Okay, so we call them saturated because they only contain single bonds. So alkanes, regardless of whether is it cycloalkanes or straight chain alkanes, they only contains single bonds. I think we have some examples over here. Okay, so we do have unsaturated hydrocarbon. That usually applies to things like alkenes, where there is at least one CC double bond, or a cyclic alkene with a cyclic structure and another CC double bond, or alkynes, commonly known as acetylene, yeah, so with a CC triple bond. For aromatic hydrocarbons have some additional stability. Yeah, examples arenes. I think only arenes will be taught to you in H2 curriculum. Yeah, so for arenes, it is actually formally a ring with 3 alternating double bonds, but because the pi electron cloud is delocalized, so we represent it with a ring right in the middle like this. Yeah, so just be very careful when you try to represent the structure. Okay, so the normal convention, the usual convention for A-level chemistry for an aromatic ring or a benzene ring, so-called, is actually a hexagon with a ring in the middle. Okay, this particular form, what we usually call calculate structure, we don't usually use that very often in H2. Yeah, but although we represent it this way, are still aware that a delocalization of pi electron cloud exists. Yeah, you will see this very often in university textbooks where they will draw it using the calculus structure because it's actually easier to draw reaction mechanism in that way. Yeah, but so if I mean H2 is not a subject on a lot of reaction mechanisms where you draw a lot of curly arrows, so we don't usually advise the students to draw it using the calculus structure. But for H3, because we do draw more mechanism than usually what you encounter in H2, usually drawing it in terms of the calculus structure will make drawing of mechanism easier and more intuitive. Yeah, so I don't think I want to go a lot into details as to why is that the case. I think if you are interested, you can actually read more. I think there are a lot of resources available online. Yep. Okay, so being saturated and consisting of only single bonds, you would expect the alkanes to be consisting of only sp3 hybridized carbon. Okay, so as we mentioned earlier on, it can either be aliphatic straight chain or alicyclic cyclic structure. Okay, so we have exercise 1.1 over here. So you are supposed to write down the general formula for aliphatic alkanes. I think this probably needs no introduction. Straight chain alkanes have two tails with one additional H's. So every carbon in the middle will have two H's. So in this case, we are looking at CnH2n plus 2. The plus 2 account for the two additional H that the carbon at the end is being bonded to. So for example, if we have a straight chain pentane, then the three carbon in the middle will have two H's. That explains why it is CnH2n, and then the plus 2 actually comes right at the end because the carbon at the end is bonded to an additional hydrogen each. Yeah. Then once you form the cyclic structure, which is a cycloalkane, you will no longer have the plus 2. Okay, because once you form the cyclic structure, that's like this, connecting them together, or we can just draw them in a nicer way, which is a pentagon. Sorry, I think this part is not so nice. Okay, so a pentagon has to be closed. Yep. So when you draw that as a pentagon, then there will no longer be plus 2 because the two H's is being taken out, and then the two extra single electron on each carbon are being used to form the sigma bond between the two ends. Yep. So therefore, the general formula of a cycloalkane is CnH2n, and you will realize that the general formula is similar to that of alkene. So you have to be a little bit careful when you are navigating through organic chemistry, because sometimes different functional group or homologous series can have the same general formula. Okay, so which class of compound is isomeric with cycloalkanes? So in this case will be alkenes. I think I just mentioned that. Yeah. Okay, so one of the other compound you can draw with C5H10 would be maybe just an alkene that looks like this. Sorry, I think too many carbons. 1, 2, 3, 4. Yeah, correct. Yeah, so alkenes that look like this, or you can have a cis trans if you wished. Okay, something like that. Yeah. Okay, so we'll move on to the nomenclature. I will not spend too much time on nomenclature because if you read about or if you saw the bridging course, I kind of mentioned a little bit about the nomenclature. So over here, I will just I'll just dive right into the not so common ones. I mean the one that's the first four that aren't very intuitive because they do not follow any of the order that we are aware of. So that's one carbon, that's meth, and then F will be 2 carbon, prop 3, and then butyl will be 4. So anything beyond that, I think you can infer them from the suffix. Okay, sorry, the prefix, not the suffix. You can infer them from the prefix. So pence will be 5, hex 6, hex 7, oct 8, nor 9, and that 10. Okay, and then if they are branch, normally I won't go into details, but let's say we have an example here. Okay, so we look for the longest chain, and then we'll just number from left to right, which is the smallest number at the branch portion. So in this case, Okay, so in this case, we can't go from left to right. Yeah, because the longest chain is actually like this. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 8 carbon in total. So if I number it from left downwards to the right hand side, the branch portion will be carbon number 5. But if we go the other way around, that's 1, 2, 3, and then 4, 5, 6, 7, 8. So that's carbon number 4. So you realize that for carbon number 4, it is bonded to an ethyl group. Okay, so basically, if you have a group with one less H as compared to its alkane equivalent, we just change the suffix to Q. Okay, like YL. So ethane will be ethyl. Okay, so fourth position is the ethyl group, so 4 ethyl octane. Okay, you might be asking, can I name it as 5 ethyl octane? Yeah, probably yes. People understand what you're saying, but if you follow the usual nomenclature, then no. Okay, so just remember that for nomenclature, you might want to take note of how to at least name simple organic molecules. Yeah, and the next example we have will be 3-ethyl-2-methyl-hexanes. So again, the longest chain, the straight chain, okay, will be hexane, right? So and then with the various groups, so that's 1, 2, 3. So 2-methyl will be a methyl group, ethyl group at the third position. Okay, so this on your own, please go and look at how it's being named. Okay, so if you have a greater number of groups, let's say you have 2 methyl groups, so we'll call it 2,2-dimethyl hexane. So in this case, 2,4-dimethyl hexane, because there's 2 methyl group at the second and the fourth position. Okay, so you use the prefix di, tri to help you indicate the numbers. Okay, so I don't think I will go into details in the naming for this, because probably in for real assessment you might not get something so complicated. Like for example, in this case, we have this seemingly complicated naming groups. We call it 1-methyl-ethyl group. Okay, actually this group has a common name in organic chemistry. Yeah, it's actually called isopropyl. Yeah. Why is it called isopropyl? Because in that case, it is a propyl group, okay, but it's being bonded through the middle carbon, okay, or what we call a secondary carbon. So we call that a isopropyl group. It's just a simplified name if you wish to know. Yeah. So I mean, if you really look at many organic texts, they don't really call it 1-methyl-ethyl group. It's just too much, too long a name, so we just call it isopropyl. Okay, for cycloalkanes, I think again needs no introduction. It takes on a certain shape, or we call conformation. Like cyclohexane, we have it as a chair conformation, which looks like this. But the details you don't have to know, because those are things, if you're interested, you can learn them in H3 lah. Okay, so I will not bore you the details over here. Okay, so you can just read up, and in the tutorials, anything we can always clarify. Okay, the next portion we're going to look at is actually isomerism. Isomerism for alkenes, again, is not that complicated, because we have been dealing with them since we started the chapter on isomerism. Yeah, so the first thing we want to look at is constitutional isomerism. So maybe let me emphasize this term again. So we are following IUPAC convention for the current H2 curriculum. So we no longer use structural isomerism. So we call it constitutional isomerism. Okay, this is just for your consumption. So you might want to use the proper IUPAC term. Okay. In this case, we have exercise 3.1. Okay. Okay. So I think here that there's an interesting examples. The number of constitutional isomers actually increases drastically. Yeah. So like any 10 carbon alkanes, you have 75. That's a lot. 20 carbon, you have like over 300,000. So I don't think you want to go and draw everything out. I think even the computers also might find it difficult to draw. Okay, then exercise 3.1, using skeletal structure, they ask you to draw out all the alkenes with the molecular formula C5H12. Wow, C5H12. They want you to draw all the alkenes. So keyword is all the alkenes. Okay, that means there shouldn't be any double bond. Okay, C5H12 obviously is saturated, because if you calculate the degree of unsaturation, remember what I mentioned to you in the introductory organic chemistry chapter. So when we calculate degree of unsaturation, what we will normally do is we will take the formula of the alkanes. So in this case, with 5 carbon, the maximum number of H you can have is 2n plus 2, that's 12. Okay, we minus off the actual number of H, divide by 2, so that's 0 in this case. So that means this compound is straight chain saturated. Yeah, if you apply the same formula to the one below, which is C5H10, you realize that the number of hydrogen is now reduced to 10. Okay, and then it has 1 degree of unsaturation. But since it has to be an alkane, the one below definitely is a cycloalkane. Okay, so this is just for your information. Okay, so do not straight away see C5H10 or like CnH2 and then you conclude that it's an alkene. It need not necessarily be an alkene. Okay, so for C5H12, as I mentioned to you in the chapter on constitutional isomerism, on isomerism in general, right? The easiest way is always to draw the straight chain. Yeah, and then we try to branch it. So we draw 5 carbon first. Okay, so there's only one possibility for this. Okay, and then we will draw 4 carbon. Okay, and then we branch on one of the carbon. Okay, then the next thing you might be thinking is, can I branch the other carbon? So can I draw this? You actually can if you want, but it's actually the same thing as the one on the left. So normally we won't draw this. And then after that, the next structure I want to look at is maybe 3 carbon, and then I branch at the same carbon, and then I branch here. Yeah, because if you are branching at the other carbon, then actually it's the same as the one on the left. Okay, yeah, so therefore there's only 3 answers to A. Yeah, so these 3 will be the answer to A. Okay, then what about B? So again, the simplest thing is 5 carbon, we'll just draw 1 ring, that's a cyclopentane. Okay, but of course there it's possible for there to be more combination because I can have a cyclobutane with a branch methyl group. Okay, or I can have a cyclopropane with 2 methyl group here and here, or even at different positions. Okay, like this. Okay, or I can even have them at the same position like this. Yeah, so altogether I will have 5 cyclic structure. Yeah, so the quick way or the fast way to work on constitutional isomerism is, I think if you remember what I said to you earlier on, is to have your own rules, have your own voice, and draw the structure out systematically, and then slowly do the branching. But I think in this case for alkanes is a lot easier. I think once I have a heteroatom like oxygen or nitrogen, I think it will complicate matters. Okay, so the next section 3.2 enantiomerism, we are going to demonstrate using alkane again. So draw the structure formula of the alkane. So remember in our in-class exercise, some of you might make certain mistakes, right? So in this class, in this case, they just want us to draw the structural formula of the alkanes with the lowest MR that can demonstrate enantiomerism. Yeah, lowest MR. So very interesting question. They don't give us any clue, any other clue. So just lowest MR. Okay, so obviously lowest MR, right? I must have a carbon in the middle, and to the best of my ability, I will have 4 different groups. Okay, because I want the lowest MR, one of the group must have 1 hydrogen. Okay, the other group maybe 1 carbon. Okay, the next group maybe 2 carbon, and then the final group maybe 3 carbon. Okay, I think that will make a lot more sense lah. Yeah, because I can't have a 2 carbon group that is branched. not possible because they'll be the same thing. Yeah. So therefore, the simplest structure I can come up with will be 2, 4, 6, 7. This 7 carbon structure. Okay. And if I'm going to, and they did not ask me to draw display formula. So, so in this case, I can actually draw it in terms of skeletal structure. So I'm going to have a carbon in the middle, okay, and a H here, okay, and maybe this is a CH3, okay, and an ethyl group, and then this will be the 3 carbon group, okay. So like this, okay, like this, and like this, okay. Yep. So I think that works. If some of you I mean, if you wish to show the groups out, because at this stage you might not be extremely comfortable with skeletal structure, that's fine. So I'm just going to erase this portion. I'm just going to erase this particular portion so that I can actually show you how to actually write it out. Okay, so I can just write this out as the H. Okay, and then this is the CH3. This is the CH3. And then this is the CH3, CH2, okay, CH2, CH3, and then this is CH2, CH2, CH3, CH2, CH2, CH3. Okay, yep. So remember, organic chemistry is very flexible. If you read the question carefully and they ask you to draw structural formula and not display formula, there are just a lot of ways or multiple ways you can represent your answers. Okay, so do not be too worried about whether you have time to finish the exams, because if you draw skeletal, I think you can always speed up and then save the remaining time for other parts of the questions. Okay, the next part I'm going to go into is physical properties. I'm not going to focus too much on physical properties as well, because you're going to learn a lot of it under I mean not you're going to learn a lot of it, but you have already encountered the bulk of it under chemical bonding, okay, which is actually learning objective of the second topic. Yeah, the different structures and bonding. And as we mentioned, the electronegativity difference between carbon and hydrogen is actually very small. So the very small difference gives it a almost negligible dipole. So we usually consider hydrocarbon as nonpolar. So them being nonpolar, that means that they are usually being held together by weak dispersion forces, or otherwise known as instantaneous dipole-induced dipole interaction. Okay, so I think this can be easily seen from its physical states. I think going from methane all the way to octane, you can see that the melting point, or rather the boiling point, actually increases quite a bit. Okay, so hexane is a solvent we often use in the laboratory. Yeah, so because it's non-polar and it's quite easily distilled away. It's a component of petro. Okay, the first 4 members are actually important members of the components of the LPG. Okay, so you might want to be familiar with them. Okay, and anyway now you know that these are actually obtained from the ground and limited resources. So you might also be interested to read a little bit more into environmental conservation and how to reduce the reliance on hydrocarbons. I think this might be some of the questions that might be asked, because in the future we want to rely less on fossil fuels. Okay, and then the boiling point is if you plot a graph, this is a simple graph you can get. Not very inspiring. I mean, nothing fanciful about the graph, just an increasing trend. But one thing to take note of is that straight chain always lies slightly higher than branched, for obvious reason, because straight chain, as you learn from chemical bonding, it has a larger surface area of contact, so the electron cloud in that sense will be more easily polarized, and there's therefore a higher chance of forming stronger dispersion forces between the molecules. Okay, so do not remember what you learn in chemical bonding. I mean, do not forget what you learn in chemical bonding, because they will come in very relevant. And once you are able to integrate them together, you realize that when you study chemistry as a whole, you don't really need to read from the first chapter to the last chapter, or from the first page to the last page. Yeah, because everything seems to be interlinked. So once you are able to find the parts that interlink, then you realize that it will greatly reduce the amount of time you require for revision. Yeah, okay, so if you look at the boiling point, all this, yeah, so it's the same kind of explanation as you have in chemical bonding. As the number of electrons increases, electron clock size become bigger and more polarizable, so higher probability of forming stronger dispersion forces. Okay, but once you branch it, then the electron clock size actually become more compact, so they are less easily polarized. Okay, the melting point tends to be related to how they are arranged in the crystals. Yeah, so I mean, in general, they follow a similar trend. So in our case here, you have the trend for all the members, all the isomers for C6H14. Okay, so you realize that as you go from a straight chain to something that is pretty compact, and then to something that is very, very compact at one end, right? The boiling point decreases in a certain manner. Yeah, but the melting point, you realize that the one with the straight chain, right, actually has a lower, or rather has a higher melting point than the rest. Yeah, that's because it is actually easier for you to pack a regularly shaped structure in the crystal lattice. And if they are packed well, that means that stronger dispersion forces could exist between the molecules. So a well-packed crystal lattice results in maybe the electron cloud being slightly closer to each other, and it leads to stronger dispersion forces because the arrangement is more regular, and there's of course a high chance for you to get slightly more extensive and slightly stronger dispersion forces. Okay, so from here you can see the trend, and you notice that it kind of affects the melting point. Okay, and alkanes are usually not very soluble in, or rather they're not soluble at all in water. So usually alkanes tend to be used as solvent themselves because they are relatively non-polar and they have low boiling points. Okay, so some of you have seen from chemical bonding from one of the demonstration which we did involving iodine, triiodide, right? So iodine actually dissolves in hexane to give you a purple solution. Yeah, so that's because iodine and hexane can form favorable dispersion forces with one another. Yeah, so that's one of the application you can have when we deal with solubility. Okay, then for density wise, obviously they are less dense than water. If not, what you observe that oil usually floats on water. Okay, so viscosity actually describes how well the the solution can flow in a system. So usually viscosity will increase with the strength of the intermolecular forces of attraction. For example, sugar solution tends to flow very slowly. I mean, they tend to be viscous because of the extensive hydrogen bonds being formed with one another. Yeah, then for the case of liquid alkanes, sometimes the longer chain one are more viscous, not only because they can form strong dispersion forces between one another, but also because the straight chain tends to get entangled with one another when they flow through. Yeah, so that creates extra resistance. Okay, yeah. And then the next part we have is exercise 4.1. So exercise 4.1 gives you the boiling point of various alkanes. So you have from butane all the way to hexane. So over here they ask you to explain why the boiling point of butane is lower than that of pentane. I think this can be easily explained because going from butane to pentane to hexane, there is an increase in CH2 units. Okay, so pentane will have one extra CH2 unit compared to butane. Hexane will have extra one CH2 unit compared to pentane. And then that means that the electron cloud size actually increases from butane to hexane, and therefore the electron cloud become more polarizable, and the more polarizable electron cloud will result in the probability of forming stronger dispersion forces. Yeah, So so if you look at it, then therefore so butane has a lower probability of forming stronger dispersion forces between butane molecules. So if I have a lower probability of forming dispersion forces, strong dispersion forces, that means that less energy is required to overcome the weaker dispersion forces. Yeah. So that explains why butane actually has a lower boiling point as compared to pentane. Yeah, so now they ask you to draw the structure of 2,2-dimethyl butane. So I'm going to draw a butane structure and then um, 2-methyl group at the second carbon. So they ask you to predict whether you have a higher or lower boiling point than hexane. Yeah, so I think one way you can do is you can scroll back and then look at whatever is being written here, but let's not do that. Okay, we can just answer it directly. Yeah, because if you look at the structure like being drawn, right, you will realize that compared to hexane, right, you will have a more compact and less polarizable electron clouds. Yeah, so therefore the surface area of contact, okay, between the electron clouds is smaller, so it leads to the probability of forming weaker dispersion forces, yeah, between the two dimethyl butane molecules with one another will be higher. Yeah, so I mean 2,2-dimethyl butane will form weaker dispersion forces, so that means that I need less energy to overcome the weaker dispersion forces as compared to that between hexane molecules. Yeah, so because of that, I wouldn't expect it to boil higher. So therefore, I expect it to have a lower melting point, sorry, boiling point than hexane. Okay, so you realize that most of the exercises, yeah, or let's say if you have a tutorial questions on the fourth section, right, on physical property, is actually highly related to what you learn in chemical bonding. So actually, without going through section 4, right, you should be able to explain most of the question. Okay, yeah. Once you have a very good gauge of your chemical bonding concepts. Okay, the next part we're going to move on is on the fifth portion, which is on chemical properties. Okay, so chemical properties generally for organic compounds, right? Combustion is the most common thing, and it's probably something we are very familiar with, because like for example at home, I mean we will switch on, or maybe not at home, but in the lab. Okay, you switch on the Bunsen flame, right? So you see the flame, yeah. So that actually involves combustion of alkane. Okay, so in that case, combustion is probably something that we are all very familiar with. Okay, and it has this particular general formula. But as I mentioned, very often to students, right, there isn't a need for you to go and memorize the formula, which takes on the ratio. I mean whatever ratio here, whatever thing here. Yeah, you can actually learn to balance it yourself, even without memorizing it. The reason why you can balance it yourself, right? Maybe I can just do a demonstration over here. Okay, is that if you let the general formula of the alkane be C, of the hydrocarbon, sorry, be CXHY, right? Then you need to be mindful that if it's a complete combustion, you are only getting CO2 as gas, and of course H2O as a liquid, okay, at room temperature condition. And the X and Y factor is only being produced once. So therefore the CO2 will follow the X here, and then the H2O will follow the Y. So in that case it's Y over 2. And then finally, because you are doing combustion, right, you need oxygen, right? Yeah, so it'll be relatively obvious that the amount of oxygen I need follows the amount of carbon I use. So XC to how many O2? So that's XO2. And then Y over 2O to how many O2? So that's Y over 4O2. So that's Y over 4. Yeah. If you wish to, you can just multiply this by the O, and then you get Y over 2O. But because I'm getting O2 here, so that will be Y over 4O2. And then that will be XCO2. Yeah, if that's more comfortable to you. All right, and some students usually get a bit upset if, let's say, I have an extra oxygen here, because they usually don't really know what to do when we have an extra oxygen here. Actually, if you have an extra oxygen here, you just need to account for it over at the oxygen site. Okay, you just need to remember to minus half off because you don't need as much oxygen as you need. Yeah, so I think there isn't a need for you to memorize any of these balancing, but all you need to do is just to be aware of balancing it using a systematic manner. Then I think it will help. It will help you a lot when you try to do the balancing yourself. Okay, yeah. I think as I mentioned, the CC and CH bond are relatively strong, non-polar. So that explains why they are relatively unreactive. And because they are unreactive, usually the reaction involve if it involves oxidation, that's usually combustion, and you need to give it enough activation barrier so that eventually you are going to get the combustion product. Okay, but combustion itself, although it's useful, right, but it's not the most useful reaction because combustion itself gives off a lot of heat and maybe light, but I'm sure hydrocarbon has a lot more other uses, which along the way you will discover and you get to know some of the limitations. Okay, so yep, highly exothermic release of heat. It has a high activation barrier. So normally if you mix methane and oxygen together, they're actually quite stable. Unless you give it a spark. The spark actually provide it with the necessary activation energy for the reaction to continue. And then the heat generates will actually continue to cause more of them to react. Okay, and remember that they only burn in the gaseous phase. Yeah, so the solid and liquid must be vaporized before they are burnt. Okay, so what we are usually afraid of is actually incomplete combustion, because for incomplete combustion, the consequence is that you will produce CO, which is actually poisonous to our health and of course the environment as well. Yeah, and of course soot, sometimes it's being produced unwanted soot, it can also pollute the environment. So I think these are some of the things we might want to be aware of. Right? Okay, and then we have exercise 5.1 over here. So it reads the complete combustion of alkanes to produce CO2 is an important exothermic reaction. Okay, fine, we know about it. Which line shows the relationship between the number of carbon atoms in the alkane and the number of moles of oxygen needed for complete combustion? So again, the thing we need to do is probably to write a balance equation. So instead of Cx Hy, we write it as CnH 2n plus 2. I thought that might be better. And then the number of moles of O2 we get, and then in the process, we will have NCO2, and then N plus 1 H2O. Okay, and then we follow the convention. We will probably need NO2. Okay, so we need NO2 on the left, and then N plus 1 over 2O2. Yeah, so if we add the two up, so this 2n over 2, so that's 3n plus 1 over 2. So 3n plus 1 over 2. Okay, so we're going to erase this portion. Okay, so from here, it seems to be a linear relationship. I don't know whether you agree. Yeah, because the number of the relationship between the carbon and O2 is always related by 3n plus 1 over 2. So it's a linear relationship. And because it's a linear relationship, we look at option B. Right. The next section we are going to look at is 5.2 on free radical substitution. This is perhaps the most important section of the whole chapter on alkanes, because I think number one, it's something new for most of you. It's not new in a sense you have not learned before in secondary school, because in secondary school you learn it as a substitution reaction involving alkanes. Okay, so that's not really new, but it's new in a sense right now you need to learn how to draw the mechanism, and you need to be aware that it is the free radical that's involved in initiating the reaction. Yeah, so that's probably something that you might want to pay attention to. Yeah, so I think in most courses they will focus a lot of attention on this particular section. So if you learn it well, I mean, it will help you to appreciate chemistry to another level. So I think the first thing we need to be aware of is that for the case of chlorine and bromine, I think the emphasis is only we are looking at chlorine and bromine because fluorine is too reactive. Too reactive in the sense the reaction might be a little bit out of control, and you're going to get a huge mixture of unwanted products. We call them byproducts. Iodine is too unreactive, so in order for us to use iodine as the reagent, we can't simply use the condition we prescribe for chlorine and bromine. So by and large, in the curriculum for free radical substitution, our focus is largely on chlorine and bromine. Yeah, so in more advanced courses, you probably will learn a little bit more on fluorine and maybe iodine. Okay, so in the presence of UV light or heat, then chlorine and bromine will undergo what we call homolytic fission. Yeah, so in the process, they will actually generate radical. And then once the radical is being generated, the reaction will be initiated, and then it will move on and on. Yeah, okay, so now let us look at the table. Okay, you're going to see diagrams like this being written throughout your organic chemistry notes. So they largely just represent, I think, number one, the reaction involved. So in this case, it involved a tertiary alkane, but it doesn't mean that only tertiary alkane reacts. Yeah, so I mean, if I have primary alkanes or secondary alkanes, it will also undergo free radical substitution. Okay, so this is just something very generic. Yeah, and of course your R groups can be either H or LQ or around or equivalent things. So with X, in this case, X is either chlorine or bromine. In the presence of UV light or heat. Now, I thought this needs mentioning because for assessment purposes, you shouldn't be writing UV light or heat. It should be either or. Yeah. So just remember that when you learn the condition, be familiar with one of the condition. I think that will be sufficient. Okay. And the hydrogen halide will be the one that's being released. So if you use bromine, HBr will be released. Okay, yeah, and then you will see this quite common, reagents and conditions. In this case, either chlorine gas or bromine liquids. Okay, so conditions will be UV light or heat, so you can choose one of them. Yep, and then for observation wise, chlorine gas usually appear as color, I mean close to colors, but if it's a bit concentrated, then yellow green or greenish yellow. Okay, you'll be decolorized, or reddish brown bromine decolorized. Yeah, so you'll be good if you are able to I won't say remember, but if you search YouTube some of the reactions involved, then you should be able to encounter free radical substitution. Okay, yeah, then let us look at the mechanism. Okay, I will go through them step by step. So I think the first step is actually the initiation step, where heating or the presence of UV light is necessary. So in the initiation step, the UV light will actually cause the chlorine-chlorine bond to break homolytically. Yeah. So in this case, we call it breaking, but then the energy supply from the UV light is actually sufficient enough to overcome the bond strength. Yeah. So it results in the homolytic cleavage, and in the process, you generate the chlorine radical. Okay, so it's represented by this fish hook arrow. So if you just want a little bit more details, you can just draw the dot and cross diagram, but please take note that dot and cross diagram is absolutely not necessary when you try to represent it in the reaction mechanism process. Yeah, okay, so the homolytic cleavage involve this bond to break like that. So I purposely use a different dot and cross to represent the electrons belonging to different chlorine, but of course, in reality, electrons do not have an identity card, so it doesn't really matter whether the electrons comes from that chlorine or this chlorine. So it just breaks homolytically. So in this case, in the process, you're going to get a chlorine radical, not one but two. Okay, why is it called a radical? Because it has unpaired electrons over here. So so that means that the radical being highly unstable, right, there will be a very high chance that they will just recombine back to give you the chlorine-chlorine sigma bond, and that is probably one of the side reaction that you expect to take place. Okay, if we very quickly go on to exercise 5.2, you are being asked why are the CH bonds unaffected. Okay, so I think the main reason is if you check out the bond energy of the CH bond, it's around 410 kilojoules per mole. Okay, but the bond energy of chlorine is about 242. You just need to check your data booklet. Yeah, so therefore the amount of energy you incorporate in the UV light, okay, is sufficient to overcome the Cl-Cl covalent bonds. Yeah, but that amount of energy is insufficient to overcome the CH covalent bond. So just take note of that. And for that matter, if you use a longer chain alkane, it doesn't have enough energy to overcome the CC covalent bond as well. Yeah, so in most cases, heating alone and as well as incorporating UV light, the amount of energy being supplied, right, is actually insufficient to overcome the CH and CC bond, but it's sufficient to overcome the chlorine-chlorine bonds, and for that matter, bromine-bromine bond as well. Yeah, so that would be a simple explanation to you usually don't expect the CH bond to be broken. Okay, and if I can mention a little bit more, the CH bonds in alkyl chain or even for large molecules are usually bonds where researchers hope to be able to allow them to react and I mean eventually find some good use in mankind. So there was a very hot area of research in the past known as CH activation. I mean it's still quite popular today, but I think nowadays the research it's more on sustainable energy. But of course, CH activation is also related to sustainable energy. So if you are really interested, you can read up on CH activation, which I mean could point you in interesting direction in the future. I mean in terms of reading or even career-wise. Okay, the next step is actually the propagation step. So the propagation step usually involve the alkane itself with the radical. So when they combine, you will generate methyl radical and HCl. Okay, and then you realize that in this process, the methyl radical will straight away be so-called consumed via reaction with another chlorine, and in the process regenerate the chlorine radical. And that's why it's known as propagation, or sometimes we call it chain propagation, because the chlorine radical keep generating in the course of the reaction, and it goes through at a very fast pace. Okay, so we're not going to study the kinetics of this reaction. Scientists have studied it. If you're interested, you can read up more about it, but it's a bit complicated when we look at kinetics of radical-based reaction. Okay, if you are interested in curly arrows, then you might be interested to know that for this case, how does the chlorine radical actually grabs the H? So if I'm going to draw the CH bond out, the CH bond also undergoes some form of homolytic cleavage. So this radical will then combine with one of the H radical. Okay, because the H radical is formed due to the breaking of the CH sigma bond, or you can view it that the presence of the chlorine radical, right, will induce the breakage of the CH bond. Yeah, so in that case, the CH bond will break homolytically, and then in the process, I will get HCl and then and a CH3 radical. So the CH3 radical looks like this. Okay, so with a radical center and is neutral, and of course the CH3 radical being formed, it will be highly reactive, and then it will quickly grab another chlorine radical, or you can view it as it will induce another chlorine-chlorine bond breakage, and in the process you will generate CH3Cl plus another chlorine radical. Okay, so as we mentioned, this is known as chain propagation. Okay, and you can view the radical as some form of a homogeneous catalyst if you want to. Okay, but I would suggest you, to read a little bit more about it if you are interested to find out more. Okay, so why is the free radical reaction known as a chain reaction? Okay, of course it's known as a chain reaction because the radical being generated in the initiation step, okay, will continue to generate more radical in the propagation step. Okay, so that I do not need any more initiation step to generate more chlorine radical. Yeah, so the generation of the chlorine radical will be self-sustaining until, of course, all the methane has been reacted. Okay, and then explain why the reaction of alkanes with halogens require only a flash of UV light. I think I've briefly mentioned that. The chain reaction, the chain propagation reaction is actually self-sustaining. Yeah, because as we mentioned, for every 2 steps, a chlorine radical will be regenerated, and then it will continue to react with more alkane, and then in the process, it will generate more chlorine radical. Yeah, so I will definitely not expose the system to prolonged UV light because you do not want too many reactive radicals to be generated at the same time, because that will actually mean that too many random sigma bonds will form, and this might result in the release of too much energy, which you wouldn't know lah. I mean, it will cause an explosion. Okay, then the final step is actually 2 radicals colliding. Any random radicals. Okay, so we have chlorine, give you chlorine gas, and then we have chlorine radical, methyl radical give us chlorine, and then 2 methyl radical to give us ethane. Okay, so that will be the last step, and then once the neutral molecules are being generated, meaning all these, and then the reaction will stop because there isn't any more radicals to begin with. So if there's no radical, there will be no reactions. Okay, if you are interested in knowing about, let's say, for free radical substitution, do we need to draw curly arrows for every single step, like initiation, propagation, or termination? So maybe I have a good news for you. You only need to draw it for initiation step. Okay, so only this step is necessary. For the chain propagation step, if you know how to draw it, or if you are very confident in your arrow pushing, you can draw these 2 if you want to. If not, then you can just leave it. For the termination step, if you want to, you can also draw in the arrows, but that's usually quite easy. So this draws the 2 radicals combined to give you the chlorine sigma bond, and then these 2 radicals combine to give us the chlorine carbon sigma bond, and then these 2 radicals combine to give us the CC sigma bond. Okay, if you wish to, you can draw them. If not, you can just leave them as they are. Okay, so let me repeat. For free radical substitution, you only need to draw in the curly arrows, the fish hook arrows for the first step, which is the initiation step. Okay, now for 5.4, I guess it will be a relatively straightforward exercise. I think the first part they ask you, state the condition used for the reaction between ethane and bromine. Yep, so the condition, I'll expect UV light, okay, either UV light or heat, and then of course in the presence of bromine. Okay, you shouldn't be writing UV light or heat or sunlight. Okay, you should choose one. Okay, usually we'll just ask the students to use UV light. Okay, and then why is this reaction described as a free radical substitution reaction? For obvious reason, because it started by having a bromine radical being generated in the initiation step. Okay, and then what does the bromine radical do? The bromine radical actually substitute H for itself. So, which means the bromine radical replaces the H for Br. And we call that substitution reaction because it's a 1-for-1 replacement. Yeah. So so the substitution, you understand the reason why, because it replaces the H free radical because the bromine radical is being generated to kickstart the reaction. Okay, so write equations to show the mechanism of the above reaction. So again, it should be pretty straightforward. So I think the first step we need is the initiation. Yeah, there isn't much space. I will just try to use whatever space I have. So for initiation, I will have bromine coming together. Okay, H. Usually we represent UV with H nu. Okay, so that's 2Br radical. Okay, and then for propagation steps, we are going to have the bromine radical combining with CH3. It's actually easier to write ethane this way. You will get to understand why. And then I will generate HBr and the ethyl radical. So this is an ethyl radical, CH2, CH3. And then the ethyl radical, just write a bromine here, will react with bromine in the process, and then it will generate the bromine radical in the course of the reaction. Okay, so just 2 steps will suffice. Okay, for publication. We're not going to continue writing until all the H gets substituted, because that's not the intention of the whole exercise. Okay, so I hope you guys understand the intention. And then for termination steps, okay, so for termination step, it's usually what I call the anything goes step. So I will just have 2 bromine radical combining, okay, to give me bromine gas or bromine liquids, or I can have 2 ethyl radical coming together, okay, to give me butane, okay, to give me CH3, CH2, CH2, CH3, okay, or I can have a ethyl radical, okay, and a bromine radical coming together to give me bromoethane. Yep, and that's it. Okay, very simple, very straightforward, but usually free radical substitution will not be tested for exams, because as you can see, it's quite easy, and there isn't a lot of content that we can test you on. Yeah, but not to worry. I think along the way you will get some interesting novel questions, so to get your hands dirty, and then yeah, you'll get to appreciate maybe free radical substitution a lot more. Okay, and I think you can see from the above that you would expect the formation of a number of byproducts, because remember earlier on I kind of mentioned that my propagation step only stops here, but if you scrutinize further, right, actually the bromine radical can technically continue to extract a H from here. Yeah, if you are sharp enough, you might realize that. Yeah, so these are what we call the byproducts, which could result in multiple substitution. Yeah, so usually you need to be aware that in the presence of excess halogen, multiple substitution has a very high chance of occurring, and you end up with dichloromethane, trichloromethane, or even tetrachloromethane. So usually if we want mono-substituted products, we will tend to start off with limited amount of the halogen involved, either chlorine or bromine, because getting multiple substitution product is not our aim. But anyway, free radical substitution is definitely not a very good synthetic step, meaning it's not a very good step to use in synthesis, because it is relatively uncontrollable. Yeah, you can't really control like which radical react with what, because usually radical chemistry it's a bit messy. Is it always the case? Actually, no. Scientists, of course, have developed controlled radical reaction, but that's not within the scope of the H2 curriculum, so usually we don't discuss them. Okay, yeah, so I think from here you can see that the methane can undergo multiple substitution, and then you end up with tetrachloromethane. Okay, then we have an exercise 5.5 over here. You were asked to suggest suitable reaction condition for the substitution of methane by chlorine in UV lights, so as to favor the production of chloromethane. So if I want to favor production of chloromethane, then it does make sense if I make use of limited amounts of chlorine, or otherwise we can say we use excess methane in our reaction. Okay, so either you say limited amount of chlorine or excess methane. That's because we want to ensure that the chlorine radical will only react with methane but not chloromethane. Okay, it's a probability game. You will definitely get some dichloromethane or even trichloromethane, but the bulk of my product is monochloromethane. Okay, of course, if I want tetrachloromethane, then I will go all out. I will use chlorine in excess, 4, 5, 6 equivalent of chlorine. I can be assured that I will almost always get tetrachloromethane. Anything in between, I think, is really difficult to control. It's not like if I add 3 equivalent of chlorine, I will get trichloromethane. Yeah, it doesn't work that way because things can get a little bit complicated and there are a lot of other things at play, which I mean we tend not to discuss at the H2 level or even the H3 level. Okay, so if you are interested, you can always read more about it on your own. Okay, next we go into the next section on the ratio of products formed with non-equivalent hydrogen atoms. Okay, so if you you might be wondering what does this mean, right? So I think I'll just use a very simple example here. So here we have propane. So if you were to draw the structure of propane out, let me just draw the carbon. You realize that the 6 H's at the end is a little bit different from the 2 in the middle. Why is it different? Because the 6 H's at the end, right, they are what we call primary hydrogens, and then the 2 in the middle are what we call the secondary hydrogens. And in order for me to get 1 chloropropane, I will need to replace one of the 6 H's at the end. Yeah, so if you simply look at it as a probability game, the ratio of 1 chloropropane to 2 chloropropane should be about 75% to 25%. Yeah, because there are 6 H's there, but there's only 2 H's that are secondary. Okay, so we get about it's about a 3 to 1 ratio. Yeah, but you know that in reality it doesn't work that way, because in reality you realize that in the course of the reaction you end up with only 45% of 1 chloropropane, but you end up with about 55% of 2 chloropropane. So why is that the case? I mean, okay, so the reason has a lot got to do with the nature of the radical being formed, as well as the probability of substitution. Because earlier on, our percentage of 75 to 25%, right, is purely based on statistics. So this is just a statistics probability of replacement. Yeah, but we know that molecules, I mean, beyond statistics, right, they are also affected by the stability of the radical being formed. In this case, we are talking about radical, so yeah, they are affected by the stability of radical being formed in the course of the reaction. So yeah, so you might notice that in the formation of 1 chloropropane, right, you are actually producing what we call a primary propyl radical, but in the production of 2 chloropropane, right, you are produced from a secondary propyl radical. Yeah, so here we are trying to tell you that there is a difference in the stability of the radical here. Okay, and that is where we need to move on to the next section, because the next section, I mean, I've used several of these terms, so you will have heard of it, but then this particular section actually gives sort of like a proper introduction. Okay, so I think when you look at a table, it's quite self-explanatory. So if I have 1 R group, we call that a primary carbon. Okay, 2 R groups secondary, 3 R groups primary, and subsequently we call the H primary, secondary, and tertiary. And the stability of the radical is actually affected by this. Yeah, so in this case, a tertiary radical, okay, that means that a radical carbon center bonded to 3 R groups is actually more stable than that bonded to 2, and a secondary radical in that case is more stable than a primary radical, and a primary radical is more stable than a methyl radical. And why is that the case? This is a little bit complicated. We won't maybe discuss too much, but you might be interested to know, or you might want to commit this to part of your long-term memory, that alkyl groups are weakly donating. Okay, this is pretty important. Alkyl groups are weakly donating. So what do we mean by they are weakly electron donating? So that means that for alkyl groups, right, they would like to share part of their electron density to the groups that they are bonded to. So especially so if the group is electron deficient. So that means that if an alkyl radical is bonded to if an alkyl group is bonded to a radical, or if it's bonded to a carbocation, so these two being electron deficient, right, then the alkyl group will share part of its electron density to the electron deficient center. But this portion is a bit confusing for most students because I think the word electron donating, unfortunately, is often being used in chemistry. It's a bit misleading because some students will think that electron donating means that they actually donate electrons, like treating electrons as though they are tangible objects. That is not the case. Yeah, so the electron donating here simply means that it will donate part of its electron densities because at the highest level of appreciating organic chemistry or appreciating chemistry, we are often looking at a delocalized model when we look at the molecule as a whole. So we look at a molecule as a whole electron cloud. Yeah, so alkyl groups have that interesting tendency to donate part of its electron density, just a bit of it, to the electron deficient center. So I think you can just understand it from this perspective first. And then the rest we can always discuss in later topics. Okay, yeah, so you might want to remember this particular statement. They are weakly electron donating, but they don't donate tangible electrons, they donate or they share part of their electron densities with the electron deficient center. Could be a radical, could be a carbocation. Okay, yeah, so in this case, remember earlier on we discussed the statistical probability. So we are saying that there are 6 primary hydrogens and 2 secondary hydrogens. So by right, the ratio should be about 75% to 25%. So that's 3:1 ratio. But in terms of stability of the radical, right, the secondary radical, as shown here, over here, right, is actually more stable than the primary radical. Yeah. So now we have the two effects fighting against each other. Yeah. So I have more primary H's, but the radical form is less stable. I have less secondary H's, but the radical form is more stable. So usually you might be thinking that therefore they kind of like agree somewhere in between. Yeah, so you get a close to 50-50% ratio. To be honest, that is just the case for chlorine because there are other aspects as to why one is formed more than the other, and if you're interested, you'll get to learn more about that in H3 rather than in H2. Okay, so I will not go into details because for bromine, true enough, you actually get a lot more 2 bromopropane as compared to 1 bromopropane. Yeah, and that has got to do with reasons beyond the scope of H2. Okay, so we will not discuss them here. Yep, so we have an exercise 5.6 over here. So you are given this pentane reacted with limited chlorine in the presence of UV light. So assuming that the monochlorination takes place and the reaction happens at the same rates at all carbon atoms, predict the ratio of the products formed. Yeah. So in this case, if you look at the phrasing of the question, you notice that it is solely based on statistics. How do we know? Because of this statement, assuming that only monochlorination takes place and the reaction occurs at the same rate at all carbon atoms. Yep, so this particular question basically just tests you on statistics. Okay, so if you look at pentane, okay, so for pentane alone, let us look at the number of unique H's. So we have HA here, which is the same as the HA here. Okay, so now there are 6 in total, so I'm just going to delete that. And then HB will be different from HA, I'm sure you know, although it's secondary. Yeah, and then HB will be different from HC. Okay, it might take you a little bit of time to appreciate why are there 3 unique H's, but you can look at it from a symmetry perspective, or you can look at it from whatever perspective that you are comfortable in. Okay, so if you take a look at the ratio of HA is to HB is to HC in total, there are a total of 6 HA because the CH3 is mirror on the other side as well. So there are a total of 4 HBs and a total of 2 HCs because there's only 2 unique ones in the middle. So the simplest ratio will therefore be 3:1. Yeah, so therefore I will choose option A as the answer. Okay, and this is also very clear because replacing HA will give me 1 chloropentane, replacing HB will give me 2 chloropentane, and HC will give me 3 chloropentane. Yeah, so that's how you should look at it. But of course, in reality, the product is not 3-2-1 because there is still the stability of stability of the radical at play. Okay, next we'll look at question 2. So you are being given 2-methyl butane, and then you were told that it undergoes free radical substitution to give 4 monobrominated or monosubstituted products, A, B, C, and D. Yeah, so maybe we try to analyze the structure of 4-methyl butane first. So we have a butyl butane straight chain, and then with a methyl group over here. So let us see how many unique hydrogens are there. So there's a HA over here, so that's 1 methyl group. And then there's also another methyl group over here, so the 2 HA are equivalent. And then we have a HB, we have a HC, and a HD. Okay, so if we take the ratio between HA to HB to HC to HD, you realize that the ratio will be 6 is to, let's say, 1 is to 2 is to 3. Yep, so this is purely based on statistical ratio. So that means that if there is a chlorine being substituted at the position of HA, based on statistics alone, right, the amount will be 6 times greater than that substitute at HB, and then maybe 3 times greater than that substituted at HC, and twice as much as that being substituted at HD. Yeah, so this is what it means when we say statistical ratio. But then you also notice that there's something else which can complicate matters, which is of course very crucial. That is actually on relative reactivity. Yeah, so if we include relative reactivity, you were told that this bullet point, the ratio of the 4 products can be found by multiplying the relative reactivity of the hydrogen responsible for formation to the hydrogen atoms, total number of hydrogen atoms. So if we include relative reactivity, right, then the ratio will now be still 6 for HA, because 6 times 1 is 6. And then HB is actually a tertiary hydrogen, so that will be 6 is to 5. Okay, and then HC is actually a secondary hydrogens, so that's 2 multiplied by 3.5, that will be 7. And then HD is another primary hydrogen, so that will be 1 multiplied by 3, so that's 3. So this would be the actual product ratio, 6 is to 5 is to 7 is to 3, if we just define them as HA, B, C, and D in this particular manner. Okay, and then the next information is that there is twice as much of C as compared to A in the mixture. And then you were told that both B and C are optically active. Okay, so if you are good in symmetry, you know that replacing HA and HC with a chlorine will result in a chiral center. Okay, so we'll try that. So if you replace HA with a chlorine, there will be a chiral center here, and then if you replace HB with chlorine, there will be a chiral center here. Okay, so let us read this again. You were told that twice as much of HC as compared to A. So because you were told that B and C are both optically active, yeah, so therefore C must be one of the two. And how can you have twice as much? Yeah, you straight away will know that this can't be C, because if you look at the ratio here, it doesn't fit anything, right? Correct? Yeah, so therefore C must be this. Because if you look at the replacement of HA, right, the ratio of this 6, okay, is twice greater than one of the numbers here. So in this case, it's twice greater than 3. Yeah, so I think from here you can straight away predict that C is actually this. Okay, so this is C, and A is actually replacing HD with the chlorine. Okay, so in this case, D will actually look like this. Okay, so this is D. Okay, and of course B will be this because you run out of options because B and C are both optically active. So if C is this, B must be the other one, and therefore the final one D must be the one with the tertiary carbon. Okay, or the hydrogen for that matter. Okay, so with that coming into play, then now they are asking you for the actual product ratio A to B to C to D. Okay, so with that A to B to C to D, then we can just plug all this in. So my B is here. Okay, sorry, my C, I think it's easier to plug C in because C is twice as much, right? Yeah, so this is actually 6 as much as A, so A is actually 3. Okay, and then D is the unique one out, so yep, so this is 5, and then this is a 7. Okay, so this will be the actual ratio. Okay, my apologies that my numbering or my labeling of letters here is different from the products. Yeah, but this is often the case, and it doesn't really matter because at the end of the day, you will get the same answer. Okay. Okay, next we are looking at the reactivities of halogens with alkanes. I think there are a lot of details on this, so I don't want to, again, it's not the purpose of H2 to go into all the great details. Yeah, you can read more about them or you can look source for more materials. Yeah, but in general, fluorine gas is extremely reactive. Yeah, extremely explosive as well because of the low FF bond energy. So the reaction will be very, very vigorous. Chlorine and bromine, as we mentioned earlier on, you require UV light or heat for reaction to take place. Okay, with bromine will be a lot slower, okay, than chlorine. Iodine usually no reactions, so if you want iodine to react, then you need to incorporate different conditions in. Okay, there is actually a way for us to analyze this, which is incorporating what we learned in energetics. So I'll just leave you to look at this particular table. So basically what happens here is that we are looking at the halogen bond energy here. Okay, and then we are looking at the CX bond energy and the HX bond energy. Because in this case, right, in the course of reaction, the first bond, the two bonds to be broken are CH and XX. Okay, so these two bonds needs to be broken, and then the bonds being formed are CX and HX. So if you actually analyze the enthalpy change of the reaction, you realize that the reaction with fluorine is actually very exothermic. So usually very exothermic reaction, as I mean in the case of such radical based reaction, they tend to be uncontrollable. Yeah. Then with chlorine, quite exothermic but not so. And then with bromine is fair, but with iodine is actually endothermic. Okay, so I think they analyze it here for you. You can either do it in such a format or you can do it in the energetics format. Is really up to you. It doesn't really matter how you analyze it. Okay, yep. So if you are to do it in our usual energetics format, you can actually view it as we can just draw one of the bond out, CH3, and then plus XX, and then you get X CH3 plus HX. Okay, so if you analyze it based on our usual energetics format, you'll be homolytic bond breakage. In this case, it gives me a hydrogen radical plus a CH3 radical. Okay, of course everything is in gaseous phase. Okay, and then plus 2x radical, 2x radical. Okay, and then of course in the process, the homolytic cleavage of this also give us two X radical, a H radical, and a methyl radical. Okay, yeah, so I think I have to put in the gaseous phase so that it doesn't confuse all of you. Yeah. Okay, so in this case, we are looking at the bond energy of CH and then bond energy of XX. Yeah, in this way, we are looking at bond energy of CX and bond energy of HX, and then this is the enthalpy change. Yeah, generally we are analyzing it this way. It's actually very similar. In fact, it's actually the same as what is presented to you below. But for those of you who like to view it in the form of a cycle, I think this might be a little bit more comfortable. Okay, yep. And then for exercise 5.7, you were told that chloroalkanes and bromoalkanes can be made by the reaction of corresponding halogens with alkanes, for example. Suggests why it is not possible to make iodoalkane in this particular method. Okay, so again, we can do the same thing if you want to, but you might want to be aware that the HI bonds formed in the first propagation step is actually a very weak bond, okay, and it's highly endothermic. If you want to, you can actually analyze it a little bit by looking at the cycle. So if we have CH3 CH2H plus I, okay, and then if you look at the, okay, so maybe it's easier to actually look at the propagation, I mean the steps here. So in the first step, we are looking at the formation of HI. So if you want to form HI, the bond energy release, the amount of energy released is actually 299 kilojoules per mole of energy. Okay, and if you release 299 kilojoules per mole and you are breaking a CH bond, we are actually looking at 410. So CH bond is 410 and this is actually 299. Yeah, so the first step is actually relatively endothermic. Okay, so if you are looking at delta H1 for the reaction between ethane and iodine, right, we are actually looking at 410 energy you require to break the CH bond and energy released in the formation of the HI bond, and we are looking at actually 111 kilojoules per mole. This is actually highly endothermic. Yeah, so a lot of energy is actually required to actually incorporate this, and even if you look at it from the thermodynamics perspective, because everything else is gaseous, right? So if you are looking at it like delta G is equals to delta H minus T delta S, you know that delta S essentially doesn't change much. Yep. So therefore, temperature is not that important a consideration, although it can accelerate the reaction. So therefore, delta G is a good proxy to delta H, or rather delta H is a good proxy to delta G. Then in that case, we are looking at a first step that is not spontaneous. Okay, so in order for you to do iodination, then I think an alternative step is actually required. Okay, then even if you are looking at the second step where it actually involves a methyl radical reacting with iodine, let's try to calculate a delta H2. So for a delta H2, right, we are looking at the formation of a Ci bond. So that's essentially minus releases 240 kilojoules per mole of energy, and in the process we are breaking an I bond, which is 151, okay, plus 151. Then we are looking at minus 89 kilojoules per mole. Yeah, so for those of you who are wondering, will 89 kilojoules per mole be sufficient energy to actually drive the reaction? Actually, the answer is no. Yeah, because if you are looking from purely a thermodynamics perspective, there's a concept known as thermodynamic coupling. So for thermodynamic coupling to take place, right, the amount of energy released in one of the steps must be sufficient to overcome those in front so that you can drive the reaction forward. or what we call it can drive otherwise non-spontaneous reaction forward. Yeah, in our case here is insufficient. Of course, we are making a lot of assumptions here. Like we're making the assumption that delta F is close to 0 and delta H is a good proxy to delta G. Yeah, but in the case here, it's actually relatively straightforward, or I mean it's reasonable to make such an assumption. Okay, yeah, so we're gonna move on. Yeah, so that's quite a heavy section, section 5. Yeah, section 5 is probably the most important section in the whole of alkane. So it's definitely something which you need to pay attention to. Yep. The final section where we are looking at alkanes as fuel, all this is partly quite a bit of memory work. So I think it's a lot of reading on your own. I'll leave the readings to you. Okay, how do you like process crude oil? Which are the fragments? These are very secondary school stuff. Okay, low boiling point and then high boiling point, and then where are the fragments, the residue, the lubricants, all this. I'll leave the readings to you. What we are really interested in is probably the applications. So or how the reaction actually takes place. So all these are probably just details for you to ponder through. Okay, there's a particular learning objective which you need to recognize that petroleum chemical feedstock is a finite source. So basically is to tell you that there is a need for you to recycle. So recycling is a very important component in our daily world now, because we have limited amount of resources, in this case fossil fuels. Okay, so these are some of the readings you can read through. I will not go through them in details, you can just read them. Okay, so what are the environmental consequences in the use of hydrocarbon? You know that in the process you actually produces carbon monoxide, NOx, or otherwise known as oxides of nitrogen, and then unburned hydrocarbon. Yeah, so usually they arise from the internal combustion engine, and then in this particular portion you need to learn how they can be removed. And why is CO undesirable? You probably will get to learn a little bit more in transition metal chemistry, but basically they bind irreversibly to the hemoglobin in the blood. Okay, and that actually depletes the oxygen supply to important components in our body. Yeah, you can read more about that. And of course, for unburned hydrocarbons, in the presence of sunlight, they will react with oxygen, ozone, and oxides of nitrogen to form photochemical smoke. Okay, which is again undesirable. And then nitrogen monoxide and nitrogen dioxide, they are known as NOx. Okay, they are actually produced in the combustion chamber of motor vehicles because the high energy or highly energetic environment in the internal combustion engine, right, possess enough energy, okay, for oxygen and nitrogen to react, and this is really undesirable in the production of NO, and then NO will get further oxidized to give you NO2. Yeah, you realize that in our normal environment we have a lot of nitrogen and oxygen around us, but they don't react, right? They do not react because when they collide, they will just bounce off like billiard balls because not enough energy to overcome the activation barrier. But once in the internal combustion engine, then there is sufficient energy. So once the barrier is being overcome, then you're going to get nitrogen monoxide and nitrogen dioxide, which is what they mention here, undesirable. So these are some of the reactions you need to be familiar with, these two. And then you probably need to know that NO2 dissolve in water to give you HNO2, which is a nitrous acid as well as nitric acid. Okay, some form of a disproportionation reaction will have taken place, and NO2 will actually catalyze the formation of SO3 by giving SO2 one of the oxygen, and in the process you get SO3, and then the NO will be further oxidized back to NO2, and then further oxidize the SO2 to SO3. So yeah, which give rise to acid rain. Okay, yeah, and then you might be interested in to read a little bit more about catalytic converter. Okay, I do suggest that you read them more on your own outside the scope of the lecture notes because they are quite interesting. So the main role of catalytic converter is to actually convert the harmful gases to gases which are not so harmful. So generally, NO and CO will react to give you nitrogen gas and CO2. You can't run away from CO2. CO2 will still be released into the surrounding, and then of course CO and O2, hopefully the CO will actually react with the oxygen in the catalytic converter to give you CO2, and then the unburned hydrocarbon will then react to give you CO2 and steam. Okay, yeah. I think you guys do not belong to a generation of leaded petrol, but anyway, some form of a lead organic compounds or methyl lead, tetramethyl lead is actually added to petrol as an anti-knocking agent. Yeah, but lead will actually poison the catalyst, but I mean, this is a long time ago lah. So nowadays all the petrol are unleaded, so we do not really need to worry about this. Okay, so there is a particular learning objective here. I mean exercise, not learning objective. I'm talking about exercise 6.1. How are the oxides of nitrogen formed in the car engine? So I think we mentioned very clearly between nitrogen and oxygen, because there exists enough activation, or rather there exists enough energy to overcome the activation barrier between them. Okay, and then the three-way catalytic systems which are fitted to the exhaust system of cars remove nitrogen oxides, CO and unburned hydrocarbons. Oxidation and reduction both involved. State whether the catalysis is homogeneous or heterogeneous. Definitely heterogeneous, because catalytic converters are usually metal-based. Yeah, so definitely heterogeneous catalysis. What reactions or reactions are catalyzed by the reduction catalyst? I think we can go back to this. Okay, so if I just remove all this, you realize that this particular reaction is actually kind of like a reduction, because your N nitrogen here being +2 is reduced to 0. Okay, so this is likely to be catalyzed by the reduction catalyst. Of course, the CO is being oxidized to CO2 lah. Okay, and then which reactions is likely to be catalyzed by the oxidation catalyst? So your CO is being oxidized to CO2, so that's from +2 to +4. Okay, and then your hydrocarbon, usually the carbon oxidation state is below +4, so it's oxidized to +4 as well. Yeah, so so these two reactions is likely to be catalyzed by the oxidation catalyst. Okay, and then name a substance which poison the catalyst. So it's lead. So remedy, use unleaded petrol. I mean it's quite idiot proof because it's all given above. Okay, so now the next part is on greenhouse effect. Again, quite a bit of reading for you guys to read about it. It's important for you to know the greenhouse gases. Okay, so what are the greenhouse gases? Please go and read about them. Most of us knows carbon dioxide, but we may not know that methane is a greenhouse gas. We may not know that water vapor is a greenhouse gas, in fact, and nitrous oxides. Okay, the man-made ones include CFCs. Okay, CFCs also deplete ozone layer because some form of free radical reaction happens in the stratosphere. So that's something that you need to be aware as well. Okay, so this particular portion explain to you the impact of methane on the environment. So do go and read about them. It's important as well. Okay, and that's about it. Yep. Okay, so my apologies that the last portion of this chapter is a bit dry, so they contain a lot of readings. Yeah, but it's good for you to read them as general knowledge, because it is actually quite important for you to be aware of some of the environmental consequence of the burning of fossil fuels, etc. Okay, so with that, we'll end this chapter and look out for the next video on alkene.